Hello, everybody. Welcome to today's lecture. So today we're going to finish up chapter 5. We're just going to talk about, we just have 5.4 and 5.5 left, and neither of them are very long, and they're both also kind of similar. So in both chapters, they basically just give us formulas, and we just have to learn how to use the formulas. So that's really all these chapters are. There's not really anything deep going on. It's just, here's the formula. Identify your numbers and plug them into the formula. Okay. I'm not really going to go through in detail how to derive these formulas because it's a little bit more complicated than the other ones, but I'll try to say kind of verbally how we would go about getting to them. Okay. So 5.4 is about savings plans and 5.5 is about loan payments. Okay. So first up is savings plans. Okay. So the idea here is, okay, maybe, when we want to make a large purchase, there's typically two ways to go about doing it. You can take out a loan and buy it that way, like for a car or something, right? You can take out a car loan and pay it off monthly. The disadvantage there is that you have to pay interest. The advantage is that you get it sooner, right? The other way would be to save for it more long term, right? To put away money every month until you have enough money and then buy it in a lump sum. So the advantage there, of course, is you're going to end up paying less overall because you're not paying interest. The disadvantage is going to take much longer to get the item. And, if it's something time sensitive, like if it's a specific car that you want, it'll be gone. If you have to save for 3 years or whatever. If it's like a house, you never know how the market is going to change over that period of time. So there's a lot of factors that go into play here. So in this one, we'll look at, okay, what if we want to do it with savings? And then the next one, we'll look at, okay, what about if there's a loan? Okay. So let's first look at the savings plan formula. So the savings plan formula, it has a lot of the same parts that our compound interest formula has. It actually has all the same letters except there's one new one. Okay, so we have F. F is the same thing it was before, the future value. Okay. Is equal to PMT, which stands for payment. Okay, so this is the new one that we have. And then we have this whole big thing here. 1 plus R over N to the NT power minus 1 divided by R over N. Okay. So there's a lot going on here. Let's think about like order of operations. How do we tackle this formula? Well, we always do what's in the parentheses first. In this case, we have brackets, right? And then if we zoom in on the brackets, we have, we should simplify the top of the fraction and the bottom of the fraction first before doing the division. So on the bottom, we would just do R divided by N, and we would have some number. On the top, there's a little more to do because we have another parentheses, which is raised to an exponent. We have division, addition, subtraction. We have pretty much everything going on here. So we'll deal with that in an example. Let's first write out what all the parts are. And like I said, these are all pretty much the same thing. F is our future value. So this is like after, if you're making payments every month or whatever, after this amount of time, you will have this amount of money. Okay. So we have our F is our future value. PMT is the new one. This is our payment. Okay. It's not often we use 3 letters to represent things, right? Usually we just use 1 letter. It's just the idea here is just that P was already taken by principal. Um, so there's not really a natural letter to use. So instead of making it more confusing, we just abbreviate payment. Okay. R is still the interest rate. Okay. So this is all assuming that when you're saving, you're putting it into an account with an interest rate, right? So if you have just like a checking account, um, or something like that, those typically don't have interest rates. Some do, but most don't. So this formula wouldn't really apply to that. We couldn't even let the interest rate be zero and get anything out of this formula, because if we let the interest rate be zero, the denominator here would be zero, and then we're dividing by zero. So it wouldn't make sense anymore. In fact, we up here, this would simplify to 1 minus 1, and then just overall, we would just have 0 over 0, which wouldn't make any sense. Essentially, if we didn't have an interest rate, all we would need to think about is the payments, because the money's not changing, right? If you're saving like $100 a month, then you do that for 3 years, all you need to do is take that 100, multiply by 36, because that's how many months would be in 3 years. And all of this just wouldn't matter anymore. So this is only relevant for accounts with interest rates. Okay. So this would be like a savings account, right? If you have a savings account, it's all savings accounts have some interest. Sometimes they can be converted to non-interest accounts after a while or something like that. But usually when you start a savings account, it has some interest. It might not be a lot. Like for example, if you just go to some random bank like Chase or Fifth Third or something, and you just get their normal savings account, the interest rate is probably something very low, like 0.01%. Something you wouldn't even really notice, like a couple of cents per year. But there are other types of accounts that will have higher savings accounts, like they call them money market accounts. Usually you need so much money in them though to open them. You could have an investment account, which again you would need so much money to open them. If you have any kind of retirement savings plan, it would follow this formula. If you knew your interest rate and when interest is applied, then if you are going to retire and say, say you open it like when you're 30, you want to retire at say like 65, then you'd put in T equals 35, your interest rate, how many times it's applied, how much you put towards it, and then that'll spit out your future value. Okay. Assuming the payment is always the same, which is a kind of a big assumption because usually over time your payment is going to change. There's also some online banks that typically offer like pretty good interest rates for just regular savings accounts. They don't have to be like money market or investment accounts or anything like that. Like Discover Online Bank or Ally Online Bank, they typically have them around like the 1% range, which is very good for a normal savings account. It's not a ton of money still, um, but it's way more than you would get at just a regular bank in a regular savings account. Okay, so I guess all this is all to say that there's a ton of options, ton of different kinds of accounts to explore. But the key thing is that we have some interest rate in order to use this formula. Okay, n is number of times compounded annually, so just like before. Okay, we already know both of these ones from last time, with T being time in years. Okay. Okay. Um let's look at the first example here. Well, first of all, actually, let me just talk about the formula for a minute. you should notice some parts of the formula, like this 1 plus r over n to the nt. That's the exact formula we had with the compound interest, right? If I go back right here, that's just the compound interest formula without the p part. So that's where it's coming from. R over n, that's just another rate. And yeah, essentially this is coming from the compound interest, and the -1 and the r over n are also coming from the compound interest. It's kind of like we subtracted 1 from both sides at some point and then divided by r over n to bring them over to this side. But like I said, we're not going to go into the full derivation of the formula. I just want to point out some parts that you might recognize. Okay. So let's look at this example just from the textbook here. Say Henry decides to save up for a big vacation by depositing $100 every 2 months, or sorry, every month, into an account earning 4% per year. Okay. How much money will he have at the end of 2 years? So 4%, first of all, like that's a lot. That's usually higher than you would get from, definitely higher than you would get from a normal savings account. Probably higher than those money market accounts like I was talking about. Money market accounts are essentially you give the bank money, they invest it, but the money is still liquid, meaning that you can still take it out. But the interest rates don't get very high on that because they are liquid. There's another type of savings called a CD, a certificate of deposit. They typically have kind of higher interest rates, but you're locked in for a certain amount of time, usually like 1 year or 2 year, or they even do have like 6-month CDs. But the interest rates usually aren't that much better. Okay, just in my experience, I used to work for a bank, so I'm just talking about like what I would see there. I didn't do a lot of research on it or anything, but still, if you do go into more like investing, like you're buying like stocks and bonds and that kind of stuff, typically long term you would average around like 7% per year. So 4% is probably more like something like that, like you're investing into like stocks or bonds or something like that, which most people only do for long term accounts like retirement. But if you have a lot of excess money, then you could invest it. You can invest that too outside of retirement accounts, and you hope to do it on average about 7%. So sometimes you might do 4%, sometimes you might do 10%, right? But just to put it in context, 4% is usually higher than your average savings account. It would probably be hard to do that without looking into like stocks and stuff like that. So let's look at our formula. Well, first let's identify our parts, right? We have our payment is 100 because we're doing $100 per month. We are doing I actually, let me rephrase n. This is better thought of in this context actually as a number of payments made. Hang on. Yeah, number of payments made per year. Okay. So instead of thinking of it like the time the interest is compounded, we'll instead think about it as the number of payments made per year. Okay, so thinking about it like that, n is going to be, we're doing this monthly, right? Every month. So n is going to be 12. Our t is going to be 2. So we're doing it, we're looking at the end of 2 years. And then our r is going to be that 4% converted to a decimal. So 0.04. So now we have everything. So we need to plug everything into the formula here. Let me just write it out again. Okay. So I'll again just do this in Excel so we can all see. I just feel like it's better than doing it on a calculator off screen. So first our R over N. We can do this all in one line, but I'll just go ahead and break it up into parts. Let's first look at what R over N is. Well, maybe I should plug the numbers in first. So we have 100 for the payment. Our R is 4, N is 12, T is 2. Okay. So let's break this up into pieces, some of the easier parts. We got to be thinking of order of operations too here. Okay. Let's do 0.04 divided by 12. We get 0.00333 repeating. Okay. That's 0.00333. Okay. You can do as many decimal places as you want, but when it's something like this, like you probably shouldn't do 2 decimal places because it's going to be 0, right? You want to at least have some significant numbers. 12 times 2 is 24, so we can go ahead and do that. Minus 1. And on the bottom, we still have 0.00333. Okay. All right, so let's go ahead, and on the top, we're going to take this number. So here's one thing we can do in Excel. We can do A1 because that's the cell. Okay. So the cells are named by the column letter and the row number. So this says take what's in cell A1, which is at 0.03. So then we don't have to do the rounding. We want to do that. We want to put this in parentheses because then we want to raise that to the 24th power. Okay. And we get 1.083143. And we want to subtract 1 from that now. Okay. So it would just be 0.08143. So we're at 100 times 0.08483, was it? Sorry. 83143. Okay. And now we're going to do, so we can take what's in A2 and subtract 1 to get our 0.083143. Now we can take what's in A3, the 0.08343, divided by what's in A1, right? because that's what we're doing on this part here. So we get 24 point all that, and then we just need to multiply that by 100. So we'll take A4 times 100. So we get 2494.29, since this is money, right? 2494.29. Okay. Should technically write a squiggly equal sign because we're approximating, because we have to round. Okay, so if he is saving $100 every month for 2 years, he ends up with $2,494. So now let's think of another question, which the book doesn't ask here, but was this account worth it, right? What was the interest really making him? Well, if all he did, so without interest, if all he did was make payments, then F would be 100 times 24, right? Because he made 24 payments over 2 years. So we'd have 2,400. So he made $94.29 extra from that. So, you might ask, is $94 over the course of 2 years worth it, right? That's only about $47 a year. Well, the real answer, the real question is, maybe it's not necessarily worth it in terms of just the monetary value. But if we think about it more as like a cost versus effort, right? It's not really taking any extra effort to put it into this account, probably. So it's basically just extra money for not really doing a whole lot different, right? Assuming you have access to an account with this high of an interest rate already. $94, it's not insignificant at all, right? It's almost an extra $100. That could go a long way, especially in the context of like being on a vacation, right? It's really just up to personal interpretation, but I would think, with the fact that it doesn't really take much extra effort, then yeah, it's worth the extra money, right? Let me also demonstrate just real quick how we could just do this all in one fell swoop in Excel. Okay. It'll just be, we just have to be really careful with our parentheses, essentially. Okay, so we want to really be careful with parentheses here. So this parentheses I just put in represents the bracket. Now we're going to do 1 plus 0.04 divided by 12, right? So that closed this parentheses. Now we're going to raise that to the 24th power. And then we're going to subtract 1. And we should put another parentheses on. No, I don't think we need to, actually. We should put this into parentheses, though, the bottom fraction, to make sure it does the division first on the bottom. 0.04 divided by 12. So we just got to be careful with the parentheses. I think everything should be good here. And then we get the same thing. Okay. So you can break it up step by step. That's what I like to do because it's just easier to digest that way. Or you can just put it in one fell swoop, but you just have to be careful of how you're grouping things. You have to make sure you're putting the right things into parentheses so that Excel knows the order to do things in. Okay. Excel is going to follow the standard order of operations. So, you use parentheses. Parentheses always goes first. So you use those to group things off, like the bottom fraction here, for example. Okay. Let us look at another example here. Example 5.42 is a good one here. Okay, this says Joe wants to buy a pop-up trailer that costs $9K. He wants to pay in cash. So he makes monthly deposits into an account earning 3.2% APR. How much should his monthly payments be if he wants to buy it in 3 years? So we're asking a different question than before. Now we want to find the payment. So we know the future value is going to be 9,000. That's how much we want to save up to. So our F here is 9,000. T we know to be 3 because that's how long we're looking at buying it in. So now we need our R and our N. Our R is the 3.2 converted to decimal. And then our N is how many payments we're making. It says monthly, so it's going to be 12 again. Okay. So let's plug everything into the formula. We're going to have to do it a little bit differently this time, though, because we're solving for the payment now, right? So we have 0.032 divided by 12 to the 12 times 3 minus 1 over 0.032 divided by 12. Okay. So what we should do, we want to get the payment by itself, right? In order to do that, we should divide both sides by this whole thing. In order to make that a little nicer, let's first calculate what this brackets is. Okay. So we'll leave this stuff alone for now. And now let's calculate what the number in the brackets is. Okay. So let me just move down here. So we can just do it all in one swoop again. So we want to do 1 plus 0.032 divided by 12, right? And we're going to raise that to the 12 times 3 power. So you should put 12 times 3 in parentheses so it knows to multiply those first before raising it. Otherwise, it'll raise it to the 12th power, and then it'll just multiply the whole thing by 3. It won't put the 3 in the exponent. So you should rope those off into a parentheses. Or you can just do 36 to make it easier. Minus 1. And I think maybe we're missing one. Yeah. Need another parentheses up here. So that extra parentheses I just added, that's for roping off the top part. I put the whole top part in parentheses so it knows that's like the top of the fraction. And now we're going to do the bottom of the fraction, also put that in parentheses to do this. Okay, so we get 37. 37.0. 0.73191. Okay. Now we're doing the payment multiplied by 37 point all that. So to get the payment by itself, we should divide both sides by the 37 point all this. Okay. So ultimately we're going to get payment, payment equals, and we can just do 9,000 divided by A14, because that's that cell. So we get 238.52. So his payment should end up being 238.52. Okay. The book goes through how to do it in the standard graphing calculator. If you'd rather do that, you can also just do it in your phone calculators. If you're doing it in the phone calculators, it's probably better to take it piece by piece, like just do one part of it, then write down the number, rather than trying to do it all at once, because that can be kind of complicated. Okay. Okay, so now we're going to move on to loans, which is almost the exact same thing. There's just a couple of differences in the formulas. Okay. So let's go over here. All right. Okay, so like I said, this section is called loans. So loans work very similarly to savings. It's just kind of it's kind of like you're just on the opposite side of it. Right? Loans can be thought of like your bank is making a savings account with you, right? You're getting the money and paying them interest. Whereas when you make a savings account, you're giving the bank the money and they pay you interest, right? So it's just kind of like being on the other side of it. And that's exactly what the formula is going to reflect. It's just going to be kind of like the same things, except for where there was a plus, there will be a minus and stuff like that. Okay. So the loan payment formula, we're going to P. So we don't have F this time. We just have P equals payment times 1 minus 1 plus R over N to the negative NT power divided by R over N. So instead of doing a plus 1, or instead of doing 1 plus this whole thing, we're doing 1 minus it, right? With the savings formula, we had 1, I'm sorry, we had minus 1. So instead of doing this minus 1, we're doing 1 minus that, is what I mean to say. Okay. Also, instead of having the positive NT exponent, we have a negative NT exponent. As a review of what negative exponents do, okay, reminder. A over B to the negative n is equal to B over A to the n. In other words, the negative exponent, it flips the fraction. Okay, it makes you take the reciprocal. So, for example, 1/2 to the negative 1 power is going to be 2 over 1, which is just 2. So it's just flipping the top and bottom of the fraction. The actual NT part would just be as normal. Now, you don't need to do it by hand anyway. Your calculator knows this, so you just have to remember to put the negative in there. Okay. It's important with the phone calculators. There's a minus sign, but you know, of course, for subtraction, you don't want to use the minus sign because that doesn't work the same as the negative sign. Instead, on the Android calculator to the left of the 0, there's a plus and minus sign. That's what you want to do to change numbers to be negative or vice versa. There's a similar button on an iPhone. I think it's the same thing with the plus and minus. It says like plus/minus. I just don't remember exactly where it is. Okay. All right. And then the bottom of here is the same. And we don't have a future value anymore because we're not saving up for the money. Instead, when we take out a loan, we're getting the money now, right? So we're looking at what's the present value of that money. Okay. So I won't write out what the letters are again because it's all the same, except here I'll write P is the present value or principal. Okay. Okay, let's say let's look at an example. Okay. It's really all there is to do with these problems is examples because we just have to look at how we use the formulas. So I'll just kind of summarize this because it's kind of long. Ed buys an iPad. The payments are $30 a month for 4 years at 14.5% APR, compounded monthly. Okay. I think that's all we need here. Right, we got our time, we got our R, we got our payment, and we got our N. So, yep. So let's see what the present value of this is. Okay. The present value here, we're going to plug in 30 for the payments. Okay. Our formula was 1 minus 1 plus R over N. R is 0.145 because we take that 14.5 and convert it to a decimal. N is 12 because we're doing this monthly. To the negative 12 times 4 divided by 0.145 divided by 12. All right, so we can do this all in Excel in one fell swoop if we are careful. See what the best way to do this is. It should be good to move it right here. I'm gonna make sure I'm not cutting it off. All right, we'll move down here now. So we want to do, whoops. We want to put a parentheses for the top part. 1 minus another parentheses for the parentheses we see there. 0.145 divided by 12. Close that parentheses. We want to raise this, and then we need a parentheses for the exponent because we're multiplying it first. Now we can close off the top parentheses. Divided by bottom parentheses is 0.145 divided by 12. Okay. And overall, I forgot we're multiplying by 30 because I kind of cut that off here, right? So this is everything. So we're going to get 1087.83. 1087.83. So that's the present value of this iPad, which is pretty expensive for an iPad. The problem mentions that the retail cost of the iPad is $500. So this is it's not a good deal, basically, right? And really, he paid even more than this, right? This is the present value, so this tells you how much it is worth right now based on the terms. But he's paying even more than this because he's paying 30 times 48, right? Because $30 payments, and he's making them 40 times, which is $1,440. Okay. So he's paying $1,440. You could say A22 minus A21. That's how much he's paying in interest, $352. Which is pretty significant considering the original price of the iPad was only $500. So he's paying almost 3 times as much for the iPad in order to do this over 4 years. Okay. So, and I mean, this is a common trap that we have to look out for, right? That's not to say that, there's not advantages here, right? The advantage is you get that iPad, which, that could be worth it to somebody. Like if they don't have a computer and they desperately need it, for that time period, maybe for school, maybe like to apply to jobs, something like that, right? It just makes your life easier. Maybe it's worth it. So there's reasons these exist, right? Because there are times when we need something like this. But if we can afford not to, it's something we should try to avoid because we're paying more than 3 times the value. I mean, almost 3 times the value. We just don't really notice it as much because it happens spread out over 4 years, right? Okay. Let's look at one more example here. This is about a mortgage. So it says Morgan is going to buy a house for $290,000 with a 30-year mortgage at 5% APR. Okay. What is the monthly payment? Pretty standard thing you'd want to know buying a house, right? Just to speak to like the numbers here, it's hard to say like if these are reasonable, right? Because houses fluctuate a lot depending on the area. $290,000 here would probably be a pretty nice house. $290,000 out in San Francisco, it would be unheard of, right? Because even even like really small houses there are getting up to like 800,000 to $1 million, right? So it heavily depends on what part of the country you're in, and all that. 5% APR though, that's pretty typical for mortgage rates around there. But yeah, in this area, 290,000 is probably pretty nice. And typically with mortgages, you can do either 30-year or 15-year. Most people do 30-year though. 15-year, the advantage is you usually get a lower interest rate, but your payments are higher, of course. Okay. So let's look at, we want to find the payment this time. So let's plug in everything we know. We know the present value is 290,000, right? So that's not actually what you're paying for the house over the amount of time. That's what the house is worth right now. So the person that you're buying it from, that's how much, the bank you're getting the loan from, that's how much the bank is paying right now, right? The bank will pay the seller $290,000, and then you're going to pay the bank back over 30 years, and you're going to end up paying a lot more than the 290,000. So we look at, this is the payment. We have 1 minus 1 plus R, which is 0.05, divided by 12 to the negative 12 times 30, much bigger than our other numbers, over 0.05 divided by 12. Okay. So let's go ahead and put that in here. So we're just putting this number in first, and then we'll do that divide both sides thing again. Okay. So we'll rope off the top with this parentheses, 1 minus, and then we have that next parentheses, 1 plus 0.05 divided by 12, raised to the, put the exponent in parentheses, negative 12 times 30. All right, and then we're done with the top, so we close that parentheses, divided by 0.05 divided by 12. So we get 186.2816. $186.2816. Okay. Now again, we want to get the payment by itself, so we divide both sides by 186.2816. Okay, so these cancel, and then we get the payment is, let's see, 290,000 divided by 828, 1556.783. Which it's money, so we round to 2 decimal places. Okay. So, yeah. So $1,556.78. Right. Pretty expensive here compared to like rent prices here. But like I said, if you go to other parts of the country, like the West Coast, especially like LA and San Francisco, their typical rent is like $2,000, or $3,000 even. So, this would look great to them, but not so good to us, right? So like I said, you know, the 290,000, that's how much the bank is paying to the seller. That's how much the seller is getting. How much are you actually going to pay over the lifetime? Well, 1556.78 times, if it's 30 years, then you're making 360 payments, right? So 1556, well, I can just do 829 times 360, whoops, times 360 is 560,000, 441.8. 560,441.8. So we think like 80 cents. Okay, almost double the value of the house, which shouldn't be that surprising because it's a very long loan, right? Mortgages are really long because it's a lot of money. So you know, this is how the banks make their money. They pay that 290,000 up front, and they get almost double that in return over the course of 30 years, right? Okay. So, I think that's good for this chapter. Let me know if you have any questions on anything. There will be a new homework soon with this information in it. And next time we will start talking about chapter 4, which is dealing with different types of growth. So how do things grow? Like, for example, how does simple interest grow versus how does compound interest grow? right? One is growing what we call linearly, the other one is growing what we call exponentially. Um, so how does that work? We'll go ahead and take a look at that next time. And yeah, thanks for watching today, and I will see you then.